Assalamu alaikum wa rahmatullahi wa barakatuh. Today, inshallah, I will solve with you some problems on different topics of chemistry. This is the first one in chemistry, so let's choose some random questions on some topics. For example, a metal plate has a circular hole in it, as shown in this figure below. As the plate is heated, what would happen to the size of the hole? So, when you heat up any metal, the atoms start to move away from each other because of the collision and the higher kinetic energy. So we would expect the size of everything to increase, including the hole. So the whole size will increase. So I will choose this one. The graph below represents the heating curve of a substance. So this is a relation between the temperature and time, or the amount of heat given to the material. What is the boiling point of this substance? When you look at the heating curve, you need to notice the different parts of the curve. At the beginning, the substance is solid. Okay, so you heat it up, you increase its kinetic energy. So in this part, let's call it part A, you increase its kinetic energy. That means you increase its temperature until you reach what we call melting point. So the temperature here is called melting point. Then you need to overcome the potential energy, which is the attraction forces between the atoms or the molecules of this solid. So during the second part, I will call it part B, there is no increase in kinetic energy, there is no increase in temperature, but you will give the energy to overcome this potential energy, and during this period the solid changes into liquid. So in the next part, which is C, the liquid will start to take the energy to increase its kinetic energy. So we expect the temperature to increase until you reach to this point. At this point, we call it the boiling point. This is the temperature at which the substance or the liquid will boil. Then it needs another amount of energy. Let's call this area D. So this amount of energy during this area or this period is to overcome the potential energy between the atoms or the molecules of the liquid. But during the period D, there is no change in kinetic energy and there is no change in temperature. So once you change all the liquid into vapor or into gas, then if you heat it up again, you would increase the kinetic energy and the temperature of the gas itself. So in this question, what is the boiling point? The boiling point is 80, while the melting point is 20. Which of the following statements is true? When water freezes, its density decreases. So let's discuss this issue. For any substance, if you cool it down, its density will increase, except water. When you cool it down below the 4 degrees Celsius, the volume of the water, because of the crystal formation, the volume will expand, the volume will increase, meaning that the density of the water will decrease. So below 4 degrees Celsius, the density of the water will decrease while its volume will increase. So I will choose this one. Let's discuss the other parts of this question too. In amorphous solids like glass, the particles have a specific geometrical arrangement. Of course not, because this is only for the crystalline solids. While the amorphous solids, they have random shapes in the order of the atoms and molecules. Number C, most of ordinary matter in the universe is in liquid state. Of course not, because most of the matter in the stars, it's in plasma state. Number D, condensation is a change of state from liquid to gas. No, condensation is change from gas to liquid, gas into liquid. while the vaporization is the change from liquid into gas. The melting point of benzene is 5.5 degrees Celsius and its boiling point is 80.1 degrees Celsius. At what temperature will both solid and liquid be present? For liquid and solid to be present, this is at the melting point. And for the liquid and gas to be present, this is at the boiling point. So here for the solid and liquid, we will choose the melting point, which is 5.5. When pure water boils, you can see bubbles rising to the surface of the water. Of what are these bubbles made? These bubbles are made of water vapor, okay? Because the water reaches to its boiling point and it turns into gas, which is the water vapor here, and it's in the shape of bubbles, so water vapor. Let's see this curve. At which portion on the graph below is the average kinetic energy of the water molecules increasing? So when he says average kinetic energy, so he means the temperature. So at which part the temperature increases? So if you look here at this graph, at F, this is an increase in temperature, and during H, this is an increase in temperature. So I would choose F and H. Which of the following expands most when the temperature is lowered? We know that when the temperature is lowered, the object contracts, except in water below 4 degrees Celsius, it expands. So I would choose water below the 4 degrees Celsius, it starts to expand. Of course, iron, if you lower its temperature, it will contract. The helium is the same. Okay, so only the water does that. Which of the following changes of state releases thermal energy? To release thermal energy, you need to go either from gas into liquid, which is the condensation, or from the liquid into solid, which is the freezing. In those two cases, the thermal energy is released. So I would say the condensation. Because melting needs energy, vaporization needs energy, sublimation needs energy. Which of the following changes of state can be identified as only evaporation? So evaporation is the change from liquid into gas, but under the temperature of the boiling. A shallow pond dries up in the summer. At 100 degrees Celsius, the water in a pan changes to a steam. 100 degrees Celsius, this is the boiling point. This is the boiling point, so that's vaporization, not evaporation. Dry ice in an ice cream cart disappears. No, because dry ice, that's sublimation. This one is sublimation. Snow on the ground turns to liquid water. So that's melting. No. So the first one, the shallow pond dries up. It dries up because water evaporates below the 100 degrees Celsius, which is in the normal weather. It happens in the summer, so that's evaporation. So I will choose this one. A student continuously heated 1 kilogram of ice until it turned to steam, and graph the changes in temperature over time as in the figure below. How would this graph differ if only 0.5 kilogram of ice were being heated? There will be no change in the temperature. Temperature is the same, but time, or some time, is, they call it the heat given to the system. The heat will be half of the heat required for the 1 kilogram. So I would choose the time of heating will be half. Okay, so we will need half of the time required for the full 1 kilogram. What do boiling and evaporation have in common? Boiling and evaporation. Let's see. Occur at specific boiling point. No. Bubbles. No, there is no bubbles in the evaporation. Bubbles is only in the boiling. Change of state. Of course, there is a change of state here, but from liquid into gas. Here he says the change of state from gas to liquid? No. So I will choose none of them. None of them. Which is unlikely contain plasma? Cloud does not contain plasma. Stars, it contains plasma. The lightning bolt, the lightning, it contains plasma, which is arc. Okay, arc plasma or plasma arc. Neon light, of course, it contains plasma. So all of these have plasma except the clouds. Density of water below the 4 degrees. We know that below the 4 degrees Celsius, the volume will increase and density, I will call it rho, density will decrease. So decreases as you cool water below 4 degrees Celsius. Increases, of course, not, is always constant, not, has highest value at 0, no, that's not right. The highest value of the density, is at 4 degrees Celsius. This is the highest value of the density. Let's move to something else, the buoyant force. To remember the buoyant force, if you have some liquid, let's say it's water, and you put some object, let's say there are 2 cases here. The object might float and it might sink down. Like if you have a piece of wood, it might float, and if you have a piece of iron, it will sink down. So what's the difference in between? The buoyant force here and there, the buoyant force is a force pushing the objects upward. The buoyant force equals the density of the liquid, which is water in this case, times the volume of the displaced water times gravity. So what's the volume of the displaced water? It's the volume of the liquid which is displaced by the object itself, which in the case of sinking equals the volume of the object, and in case of floating equals only submerged part of the object, which is this part. So this is the buoyant force. Rho of the liquid, which is here water, volume of the displaced part, and G is 9.8 as we know. In both cases there is weight which is downward, that's the weight of the object, and that's the weight of the object in these cases. In the case of floating, the buoyant force equals the weight of the object because it's in equilibrium. While in the case of sinking, you cannot say that, but you need to apply Newton's second law. The weight minus the buoyant force equals mass times acceleration, because there is no equilibrium in this case and there is acceleration which is downward. So most of the problems are about floating. So take care that during floating, the weight of the object equals to the buoyant force. And the buoyant force in all cases equals rho of the liquid times the volume of the displaced water times gravity. And again, the volume of the displaced part equal to the volume of the object if it is sinking, and only the submerged part of the object if it is floating. So let's go back to our problems. A block of iron sinks in a lake while a block of wood of the same size, so they have the same size, floats as shown in this figure below. Which of the following statements about the buoyant force? Let's calculate the buoyant force for both of them. Buoyant force here and buoyant force. We said buoyant force is rho times G times V. Rho of the water, so both they are immersed in water, so rho is the same for both of them. Gravity is the same for both of them. But what about the displaced volume here? What about the volume which is displaced in both cases? In the first case, in the one which is totally submerged inside the water, the volume of the displaced water equals the total volume of the object. While in the one which is floating, only part of the volume, so only this part is the submerged under the water. So the buoyant force of the one that sink down is greater than the buoyant force of the one that is floating. So the buoyant force of the iron, which is this one, is greater than the buoyant force on the wood block. An object suspended from a spring scale is lowered into a pail filled to the brim with water. So there is a pail filled to the top or to the end with water, and 4 Newton of water overflows. So when you put this object inside, you hang it by a scale. Okay, so some water overflows, some water will overflow. Okay, what is the volume of the water that will overflow? It equals to the volume that's submerged inside the water. So the volume of the water equals to the volume of the object. The scale shows that the object weighs 6 Newton in water. So the scale reading is the tension here. And there are other forces acting on the object. There is the weight of the object, and there is a buoyant force which is upward. So the 3 forces are balanced. So we can say T, which is the tension, which is the reading of the scale, plus the buoyant force equals the weight of the object. So the reading equals the weight minus the buoyant force. So here the reading, it was 6 Newton in the water. And he's asking now the weight of the object outside the water is what? So he gives us some hint here. There are 4 Newton of water will overflow. Let's see the water that overflows here. We said the volume of this water equals to the volume of the object. What about the weight of this water? The weight of the overflow water. The weight of this overflow water is its mass times gravity. And we know the mass is the density times the volume. So it's rho V G. Rho is the rho of water. V is the volume of the overflow water, which equals to the displaced water by the object. So this is the displaced water by the object times G. This buoyant force is rho times V displacement times G. So the buoyant force equals to the displaced water. So which is 4 Newton in this case. So this one is 4 Newton. So he's asking what is the weight of the object outside the water, the real weight of the object, which is W naught. So W naught I can see it's T plus buoyant force as we said before here, which is 6 plus 4 gives us 10 Newton. So the result is 10 Newton. A block suspended by weighing scale weighs 5 Newton out of water. So this is the weight of the object, which is W naught, 5 Newton outside the water. When it is submerged into water, the scale reads its weight as 3 Newton. So the reading of the scale, which is the tension here, is 3 Newton. How much buoyant force acts on the block? As we said before, if you have some liquid and you submerge something here, which is hung by a scale, we have some forces. We have the weight of the object downward. We have the tension, which is the reading of the scale, and we have the buoyant force upward. So T plus buoyant force equals to the weight or the real weight of the object. Here he gives us the real weight 5 Newton, and he says the scale reads 3 Newton. So this is the tension 3. So the buoyant force I would say equals 5 minus 3, which is 2 Newton. So this is the buoyant force 2 Newton. Okay. A stone is thrown into deep lake. As it sinks deeper and deeper into the water, the buoyant force on it. So if we have a deep place like the lake or something, and it's filled with liquid. If something is submerged and it sinks down, what's the buoyant force? Buoyant force, as we said, it's rho of the liquid, which is water here, times gravity, which is g, times the volume of the submerged part. So the volume, as long as it sinks down, so the volume is constant. So rho is constant, g is constant, volume is constant, so the buoyant force is constant. So it remains the same, it does not increase, it does not decrease. Okay? A beaker that is completely filled with water weighs 30 Newton, as in the figure below. What would be the reading of the scale when 5 Newton block of wood floats in it? Of course, this beaker is filled of water to the top. Okay, so when you put some object like the 5 Newton of wood, some water will overflow and it spilled down. Okay, so what is the volume and what's the weight of the spilled water, this overflow water? What's the weight of this water? The weight is m times g. And we know that mass is rho, which is density, times the volume of this water, times the gravity. So the weight of the spilled water, the water that left this beaker, is the rho of water times the volume of the overflow water times g. How much volume do we have here? The volume of the spilled water equals the volume of the submerged part of the block, which is the volume of the object under the level of the water or under the surface of the water. So as we know, the buoyant force equals rho of the liquid times the displaced volume times g. So in this case, the buoyant force equals the same weight of the water that is overflow. So they are equal. And we know, like 10 minutes ago, that if the object floats on water, so there are two forces, the weight of the object downward and the buoyant force upward. So we can say also the weight of the object, which is 5 Newton in this case, equals to the buoyant force. So it equals to, the buoyant force equals 5 Newton. And the buoyant force equals to the part of the water that is spilled. So that means we lost some water. The weight of this water is 5 Newton. And also you add a weight, which is a block of wood, which is also 5 Newton. So you lost 5 Newton and you added 5 Newton, so there will be no change to the total weight of the water. So it will give you the same reading, which is 30 Newton. If 0.98 Newton buoyant force acts on a wooden block while it's submerged in water, what would be the mass of the displaced water? Water here in a container, and an object floats on this water. Of course, we have the weight downward and the buoyant force upward. And we know the buoyant force equals rho times g times v. Rho of the water, g is 9.8, times the volume. So this is the volume of the displaced part of the water, the volume of the displaced part of the water. Of course, rho times g is, rho times v equals the mass of the water, or the displaced water, the mass of the displaced water here, times g gives you the buoyant force. So the buoyant force here is 0.98 equals the mass of the displaced water times g, which is 9.8. So the mass is 0.98 divided by 9.8. For the pressure means force over area. Generally the force in Newton and the area is square meter. So that's in Newton, the unit is in Newton over square meter. Newton over square meter, we call it Pascal. So this is the SI unit of pressure, it's Pascal or Newton over square meter. So generally speaking, the pressure equals the force over area. So in this problem, when holding a tack between your thumb and index fingers as shown in this figure below, which pressure is more? The pressure on your index or the pressure on your thumb, or both are the same? At the beginning, from Newton's third law, there are two forces equal in magnitude and opposite in direction. One is on your thumb and the other is on your index finger. So what about the pressure? We said the pressure is force over area. So the force over area 1, you see the head of this tick is smaller than the base of the tick. So we can conclude that when the area is small, in this case, the pressure will be high. So we expect the pressure, or we conclude the pressure on the index is higher than the pressure on the thumb. Pascal law or Pascal principle. Pascal said that the pressure transfers an incompressible liquids like oils, for example. So if we have a piston, let's say we have a cylinder here, it's filled of liquid and it has two sides, and in each side we have a piston. This is a piston 1 and this is piston 2. 1 and 2. As you see, the area of the piston 2 is greater than the area of piston 1. So here the pressure at this point equals the pressure on the other side. So the pressure equals force over area. So the pressure here, or over the first piston, which is pressure, let's call it F1 divided by A1. So the force on this piston, if it is F1, so the pressure is F1 over A1. And on the other side, it's the same pressure. But here it's F2, if the force is F2, divided by A2. So we can say that F1 divided by A1 equals to F2 divided by A2. So this is Pascal principle. So as the force, or as the area of the piston is small, the force also is small. And if the area is big, so the force also is big, because it's a ratio between both of them while the pressure is constant. So let's look at this problem. A hydraulic lift is used to lift a heavy box that's pushing down on a 5 square meter piston with a force 2000 Newton. What force needs to be exerted on a 0.05 square meter piston to lift the box? So we have a simple hydraulic device. It has two sides. There is a piston on the first one. The force number 1 is 2000 Newton. The area of the piston is 5 square meter. On the other side there is another piston, smaller one, with a force, let's call it F2, and the area E2 is a smaller one, 0.05. So we expect that the force F2 is smaller because its area is smaller. As the two pressures are the same, that's Pascal principle. So F1 divided by A1 equals F2 divided by A2. Let's substitute. F1 is 2000, A1 is 5, and A2 is 0.05. So what's F2? So F2 is essentially 20 Newton. So I would choose this one. Pascal's principle states that pressure applied to the fluid is transmitted through the fluid. This is Pascal principle. So the pressure is transmitted through the fluid as long as the fluid is incompressible, and most of the liquids are incompressible. A car on a 25 square meter hydraulic lift platform weighs 15,000 newtons. So we have also a hydraulic system. The big area, which is 25 square meter. This is the area. And take care of something which is very important. Now he's giving us the area. Sometimes he gives you the radius, only the radius of the piston. If he gives you the radius of the piston, so you need to get the area from the equation. The area equals pi r square. So take care, that's very, very important. If he gives you the area, so that's fine. You can use it directly. But if he gives you the radius of this piston or the diameter of the piston, you need to get the area from this equation, pi, which is 3.14 times r square. So we need to take care of this one. So again, the area is 25 square meter, and the force, which is the weight of the car, is 15,000 Newton. If the force on the smaller piston requires to lift the car is 1/100 of its weight. So the force here is 1/100 of its weight, which is 15,000 over 100. That's 150 Newton. What is the area of the smaller piston? It should be the same ratio. You need to divide also the area over 100, or you can use the ratio force over area. So 15,000 over the area, which is 25, gives you the other force, which is 150, divided by the first area. So I would say the first area equals 0.25 square meter. Okay. Next is Bernoulli principle. Bernoulli principle, he worked on the dynamic flow of the liquids in tubes. For example, he says, like if there is a flow of a liquid, so there is a relation between the area of the tube and the velocity of the liquid. The flow rate of the liquid is constant. If you enter, let's say, 1 liter per second from this side, so I expect also 1 liter per second from the other side, because it's the same tube. So if 1 liter per second enters from the left hand side, it should be output from the right hand side. The flow rate is area times velocity. So the area 1 times velocity 1 of the fluid equals area 2 times velocity 2 of the fluid. So that's called continuity equation. So that's the first part. If you try to restrict the flow of the liquid, its velocity increases. Okay? Like what happens in the hose. When you press with your finger on the hose, the speed of the fluid or the speed of the water increases, so it reaches higher distances. So let's go to this problem again, which uses Bernoulli's principle. Hose end sprayer, like when you try to restrict the water with the end, when you press on the end of the hose, okay, the water sprays and its speed increases. So that one is Bernoulli's principle. Piston, of course, it's Pascal principle. Skateboard, of course not, and buoyancy is Archimedes, if you remember this. So again, in this tube, if this is a tube, if the area increased, the velocity decreased, and if the area decreased, the velocity will increase. What about the pressure? Also, the pressure and the velocity, they are opposite to each other. If the velocity increases, the pressure inside the tube will decrease. Like in this case, if this velocity is very low, so I expect the pressure to be high. And on the other side, if the velocity increased, if the velocity here is high, so I expect the pressure in this area to be small pressure. Okay? So let's see some problems that might include the pressure as well. Let's see this one. A liquid with negligible viscosity flows through a pipe shown in this figure. This is an overhead view. So it's like a horizontal pipe. At what point the pressure of the liquid is highest? We know that the pressure is high when the velocity is low. And we know that the velocity is low when the cross-section area, when the area is high. So let's see, he is asking about the highest pressure. The highest pressure means lowest speed or highest cross-sectional area. Where is the highest cross-sectional area? It's at 0.4. This is the highest cross-sectional area, so I would choose number 4. Rank in order from highest to lowest the liquid heights H1 to H4. What's the relation between the pressure at each part, and the height of the liquid? Of course, if the pressure is high, it will push the liquid down. So if the pressure is high, the height will decrease. So the relation between the pressure and the height is inverse proportionality. If the pressure increases, it will push the liquid down, so the height will decrease. So this is the first one. What about the relation between the pressure and the cross-sectional area of the tube and the velocity? We know that if the area increases, the velocity will decrease and the pressure will increase. Okay, so we can say, like, roughly the relation between area and pressure, they increase together or they decrease together in this case. So the higher the area, the higher the pressure, the lower the height. So we can say directly area and height are inversely proportional. So the higher the area or the bigger the area, the smaller the height or the lower the height. So let's see where is the biggest area. The biggest area actually is the space, because this is like there is no constraint here. So I would say this one has the highest area, means the H will be the smaller. So H1 is the smaller. Where is the smallest area? The smallest area is here at H2. So I would say H2 is the bigger one. So H2 is the higher one because this is the lowest pressure. Then at H4, that's next one, and then H3, this is the next one. And where there is no constraint here, I would say like the area is very, very, very large, so the H will be very, very small. So that's how we order them. Something similar here, gas flows through a pipe as shown in the figure below. The pipe's constant outer diameter is shown, but you cannot see into the pipe to know how inner diameter changes. Rank in order from largest to smallest the gas speeds V1, V2, V3. So we need to find the gas speeds. We said before, if the height is low, that means the pressure is high. So pressure number 3 is the highest pressure. Then pressure number 1. So let's rank the pressure first. Pressure 3 is higher than pressure number 1, higher than the pressure number 2. What's the relation between pressure and the speed? Pressure and the speed, they are inversely proportional. Again, the relation is not very easy like this one, but roughly they are inversely proportional to each other. So I would say for the velocities V3 and V1 and V2, the relation will be V2 is greater than V1 greater than V3. Okay, which is this one. V2 is greater than V1 greater than V3. For this one, rank in order from largest to smallest, that's about Pascal. The magnitudes of forces F1, F2, F3 required for balancing the masses shown in the figure below. Note that the area A1 is less than the area A, and friction is negligible. So in this case, for any of the three hydraulic devices, the pressure here, the pressure here equals the pressure in this point, equals the pressure in this point, equal the pressure on the other point. So you can say that 500 kilogram times G, that's the weight, divided by the area, this is the pressure, equals to the pressure on the other side, which is F1 divided by A1. And also for the second device, the pressure here equals the pressure on the other side, equals the pressure on the third side. So you can say that 600 kilogram times G, which is 9.8, which is the weight here, divided by the area A, equals the force F2 divided by the area A1. Okay, and here also it's A1. And for the third device, the same issue. The pressure on both sides are equal. So 600 kilogram times G divided by area A equals the force F3 divided by A1. So if you, it's easy to find that F2 divide, this one is F3, sorry. F3 divided by A1 equals F2 divided by A1. So I would say F3 equals to F2 because the other side is the same. Okay. For the first one, how to compare the first one to the other two? They are 500 over A. 500 over A. The numerator here is lower than the numerator on the other side. So I expect the force F1 to be smaller than the force F2 or the force F3. So the force F1 is lower than F2 and F3. So I would choose the first one, that F2 and F3 are equal and both are greater than the force F1. This one is 4 Pascal 2, mass A and B rest on very light piston that enclose a fluid as shown in this figure. There is no friction between the pistons and the cylinders, they fit inside. Which of the following is true? Before we look at the choices, here we have piston, two sides. This is a large area and the other one is a smaller area. Okay, so expect the mass, if they are in balance, the mass MB to be greater than the mass MA. So here I would choose mass B is greater than the mass A because the area here is greater than the area on the other side.